This lecture continues the description of the law of inertia. At the end of the last portion of this lecture, I went through the important conceptual example of an orbit. Isaac Newton himself uses that conceptual example as a means of linking in between the following two seemingly very different physical phenomena: motion near the surface of the earth and celestial motion, motion in the heavens, if you will. As we'll see later on in this unit, Isaac Newton illustrates that those two types of motion are actually the same thing. However, before we begin to move further and get into those details, what I want to do here at the beginning of this portion of the lecture is describe to you exactly what it was that motivated Galileo to discover the law of inertia. Galileo firmly believed that Copernicus was correct. Recall that Copernicus hypothesized that the sun is at the center of the solar system and all of the planets, including the Earth, orbit the sun. Remember from the earliest unit of this course, with the exception of AP Physics students, recall from the earliest unit of this course that this then ultimately describes the orbits of the planets about the sun with simplicity, culminating with the discoveries of Kepler's laws of planetary motion. However, what was Galileo's motivation for discovering the law of inertia? Well, if you assume that Copernicus is correct, this then means that the Earth is in motion as it orbits the sun. 400 years ago, a perfectly legitimate question to ask, however, was the following. If the Earth truly is in motion as it orbits the sun, why don't we feel its motion? There's no obvious answer to that, so then therefore Galileo essentially seeks out the answer. He's motivated to answer that question and then therefore provide further support to the Copernican theory of the solar system. The physical explanation as to why the Earth is in orbit about the sun, yet we don't feel its motion, is actually quite simple. It's nothing more than a combination of the law of inertia and Galilean relativity. This is why Galilean relativity is so important from the previous unit. Now, to illustrate, let me set up the following very simple scenario. Let's say that we have two what are called inertial reference frames. An inertial reference frame is a reference frame at a constant velocity. Let's consider one of those reference frames to be at rest. For example, if you were here sitting in my classroom, we can consider the classroom to be at rest, or you sitting at your desk at home. And then the second reference frame is going to be me. I'm going to move at a constant velocity relative to you. I'm just going to walk behind the desk here at a constant speed in a straight line. And I'm going to take an object here. I'm going to use this paper clip, and I'm just going to toss it like so. So I'm going to move at a constant velocity relative to you, and I toss the paper clip straight up, and then according to me, it comes straight back down. I see a one-dimensional version of free fall in the vertical direction. However, what is it that you see about the paper clip? Well, you see a two-dimensional projectile from your inertial reference frame like so. Why don't I see the horizontal component of the velocity of the paper clip? In other words, why don't I see its horizontal motion? The reason for that, very simply, is that I'm already moving with it horizontally. So then therefore, relative to you, I have the same horizontal velocity as the paperclip does. This then means that according to me, all I see is the paperclip move up and then move down. Nothing more than that. Here's a way in which you can test this for yourself very easily. Let's say, for example, that you're in a car and you're going down the freeway at a constant speed in a straight line. So you're at a constant velocity, you're an inertial reference frame. And then you sit at your seat and you just do this. According to you, the paperclip goes straight up and then comes straight back down. Consider, however, what the situation would look like for somebody sitting outside of the car watching you go by at a constant velocity relative to them. They would then see the two-dimensional motion of the projectile. They would see both the horizontal and vertical components of the velocity of the paperclip. You don't see the horizontal component, however, because you're already moving with the paperclip horizontally. Simple as that. So then therefore consider the following. For example, right now, as the Earth orbits the sun relative to the sun, the Earth is actually moving at an orbital speed of 30 kilometers per second. But so are we. We're already moving with the Earth at that same speed relative to the sun, so then therefore we don't feel its motion. Here's another example of that. Consider the Earth's rotation. Recall that the Earth rotates from west to east. Relative to the Earth's axis of rotation, at this latitude here in Los Angeles, our speed relative to that axis is around 350 or so meters per second. Why don't we feel that motion as the Earth rotates from west to east? Very simply, we're already moving with the surface of the Earth at that same speed relative to the axis. However, if the Earth was to all of a sudden stop rotating right now, don't worry, it's not going to, but if it was to stop rotating right now, what would happen to all of us here at the surface of the Earth? Well, we would keep moving to the east at a relative speed of 350 meters per second. That is relative to the Earth's axis of rotation until a force was exerted upon us, slowing us down. That's where the law of inertia comes into play. There is no such thing as absolute rest. There is no such thing as absolute motion. There is only relative motion. So right now, relative to the sun, the Earth and all of us with it are moving at a relative speed of 30 kilometers per second. The entire solar system, it turns out, however, is orbiting about the center of the Milky Way galaxy. Relative to the center of the Milky Way galaxy, the entire solar system has an orbital speed. I believe it's somewhere in the neighborhood of around 50 kilometers per second. We don't feel that motion, very simply, because we're already moving with the entire solar system. Right now, the entire Milky Way galaxy is actually moving towards its nearest big neighbor. That's this galaxy here. This is a nice photograph here of the Andromeda Galaxy. The Andromeda Galaxy is about 2.5 million light years away. Right now, the two galaxies, the Milky Way and Andromeda, are moving towards each other with a relative speed of about 75 kilometers per second. In a few billion years or so, those two galaxies are actually going to begin to collide. However, we don't feel that motion of the entire Milky Way galaxy because, very simply, we're already moving with it. So the combination of the law of inertia with Galilean relativity provides for us an easy and simple explanation as to how the Earth can be in motion as it orbits the sun, yet we don't feel its motion. Simple as that. Okay, let me move this off to the side. Okay, now, getting back to the law of inertia, we still have this blank space here in front of the word force to fill in. I'm going to start to move us towards doing so now here in this portion of the lecture. In order for us to arrive at that point, however, I have to describe for you first the following terms: mass and weight. Mass and weight are not the same thing. From this point forwards, don't get the two confused. First of all, mass. Somewhere along the way in some previous science class, undoubtedly your teacher told you that mass is the amount of matter that an object contains. That's not correct. Instead, very simply, mass is the measurement of inertia. For this reason, it is sometimes referred to as inertial mass. Now, let me illustrate exactly what I mean by inertial mass with a simple demonstration. I'm going to use the air track, which is here on my desk. I have to tilt my phone, however, such that you can see it. So bear with me a moment. Okay, like so. There we go. Okay, now I'm going to set up a simple situation here involving some carts. So take a look at this blue air track cart right here. There's a length of string that's attached to it. And then I have here hanging off the other end of the string this little gold object. I'm going to go ahead and take the cart here and set it onto the air track like so. And then right over here, I'm going to go ahead and then drape the string over this pulley, which is off to the side like so. And the gold object here is now hanging off to the side. Let me go ahead and turn on the air, thereby removing the force of friction. And then let's examine the acceleration here of the blue cart. Okay, like so. Okay, now let's make a comparison between the acceleration that you just saw and now what happens here with this gold cart. So the gold cart also has string attached to it like so. I'm going to go ahead and take the string here and drape it over the side of the pulley. I'm going to attach the gold object once again like so. It's the same gold object as before. Okay, now let's compare the acceleration here of the gold cart to that of the blue cart from a few moments ago. Notice that the acceleration of the gold cart, very obviously, was greater than that of the blue cart. So then therefore, let me ask you this. Which of the two carts, blue or gold, was harder to accelerate? Obviously, the blue cart was. In other words, the blue cart has a greater tendency to remain at a constant velocity. Therefore, it has a greater inertial mass. That is what is meant by inertial mass. Mass, very simply, is the measurement of inertia. The greater the mass of an object, the harder it is to accelerate, the harder it is to change its velocity. Okay, let me go ahead and tilt the phone back so that you can see the board more easily once again. Okay, there we go, like so. Okay, mass is considered to be fundamental to nature. It is a new quantity for us, so let's go ahead and check the units. First of all, in the metric system. In the metric system, there are actually two unit systems. The primary unit system that most people use, and what we will primarily use in this class, is what is called the metric SI system. SI in French stands for System International. Okay, now in the metric SI system, the standard unit of mass is the kilogram. Right here, for example, is 1 kilogram. As you can see, however, a kilogram is rather large. So then therefore what we do is we take the metric SI system and we introduce into it another system. This is called the CGS system. The base unit of length in the CGS system is the centimeter. The base unit of time is the second. And the base unit of mass is the gram. This is in the CGS system. As you're undoubtedly aware of, however, from chemistry class, for example, 1,000 grams is equal to 1 kilogram. So there are actually two unit systems within the metric system. In the metric SI system, by the way, the base unit of length is the meter and the base unit of time is the second. Okay, then we also have the Old English or imperial system, as it's called. In the imperial system, the base unit of length is the foot, the base unit of time is the second, and the base unit of mass is what is called the slug. One slug is actually rather large. I don't have one here in my classroom for reasons as you'll see, but in order for me to do so, let me describe to you now what is meant by weight. Okay, as I said earlier, weight and mass are not the same thing. Weight, very specifically, is the force of gravity exerted upon a mass. Okay, now this is a new quantity for us as well, specifically force. This is your first example of a force, the weight of an object. When talking about weight, the force of gravity is equal to the mass of the object multiplied by g, acceleration due to gravity. Now this is a new quantity, specifically an example of force, so let's once again go ahead and check the units. Okay, first of all, in metric SI. In the metric SI system, we have mass in kilograms, and then we're multiplying that by g, which is acceleration in terms of meters per second squared. A kilogram meter per second squared is given its own symbol. It is referred to as a Newton, which is abbreviated as capital N. Okay, in the CGS system, mass is in terms of grams, and then multiplied by acceleration, which is in terms of centimeters per second squared. A gram centimeter per second squared is also given its own name. It's referred to as a dyne. However, primarily in this class, we're going to be working almost exclusively in terms of newtons. Every now and then, however, you will encounter the old imperial system as well. Okay, in the old imperial system, we have mass in slugs, and then we multiply that by g, which is in terms of feet per second squared. A slug foot per second squared is also given its own name. Do you know what it is? It's a pound. So for example, if you weigh 160 pounds, you weigh 160 slug foot per second squared. Okay, now this allows us to understand, by the way, exactly what is meant by one slug. One slug is equal to 1 times 32 feet per second squared, which is 32 pounds. So 32 pounds is basically the object, if you will, that is describing the base unit of mass in terms of the old imperial system. This is one of the reasons why the old imperial system is very cumbersome and clunky, and we don't use it that much anymore, especially in the sciences and in engineering. No one uses it whatsoever, even though we still use it in some common everyday language, like for weighing up ordinary objects, describing distances in miles, and so on and so forth. That's about it. However, pretty much worldwide, nobody else uses the imperial system because it's very clunky to use. Okay, now let's go ahead and take a look at the demonstration that I performed here a few minutes ago involving the air track in some detail. When we do, this will then allow us to understand how we can fill in the blank space in front of the word force. Okay, so air track demonstration. Okay, so let's draw out a simple diagram of this situation. Okay, we have this horizontal air track like so. Okay, and then here's our cart like so. Our cart will have a mass M. It's attached to the string, which is then draped over this pulley here off to the side. And then right over here was this little object, as we saw, like so. Okay, let's describe the situation when the air is off. Okay, when the air is off, as you saw earlier, the cart was stationary. The acceleration is equal to 0. And now what I'm going to draw here is your first example as to what is called a force diagram. It's also sometimes called a free body diagram. A free body diagram or force diagram is a vector representation of all of the forces that are acting upon an object. Okay, when the air is off, there are 4 forces that are acting upon the blue or the gold cart. Let me begin to describe those forces with this force diagram. Okay, first of all, we have the cart's weight straight downwards, like so. That force is obvious. There are also some other forces acting upon the cart that are obvious. We also have, for example, the string pulling to the right-hand side of the cart. Forces associated with strings and wires and so on and so forth is usually referred to as tension. Okay, and then we have the force of friction acting upon the cart, preventing it from slipping. In which direction on my diagram here does the force of friction act? To the left-hand side. So, okay, these 3 forces here acting upon the cart are rather obvious, but there is a 4th force as well. Somehow the track itself has to be pushing upwards upon the cart. Now, it's not immediately obvious where this force comes from. I'll get to that a little bit later on. However, it is easy to recognize that that force has to be there. Because if it wasn't there, for example, like so, what would then immediately happen to the cart? It would begin to accelerate downwards in this direction. Obviously, it's being prevented from doing so by the track. So somehow the track itself has to be pushing upwards. Okay, now take a look at this force diagram and then add the vectors together. Pretty obviously on my force diagram, what happens mathematically to all of these vectors? That is, what is their vector sum? It's obviously 0. The forces all cancel out. Vector sum is 0. Okay, and then I turn the air on, and this then removed the force of friction. So now let's say that the air is on. So now we remove friction. When we remove friction, the force diagram changes. Instead of 4 forces acting upon the object, now there are only 3. So we still have the weight straight downwards. We still have the tension to the right-hand side. We still have the track pushing upwards. However, we no longer have the force of friction present, and then therefore the cart accelerates to the right-hand side. Okay, we're just examining this qualitatively with no mathematics whatsoever yet, but now just take a look at my force diagram. Do all of the forces cancel each other out as they did upward on the top board, rather, when the air was off? Obviously, the answer is no. The vector sum in this case is not 0. The vector sum of the forces is not 0. In other words, these forces here acting upon the cart, they add up to some number, whatever it is. That number is referred to as a net force. The word net in mathematical lingo means sum. We say a net force is present. When a net force is present, in other words, the forces don't cancel out. When a net force is present, then acceleration occurs. So then therefore, let's now take a look at the law of inertia, still up here on the top board. At this point, pretty obviously, what is the word that fits into the description of the law of inertia in front of the word force? It's very obviously net. So if a net force is not present, then all of the forces add up to 0 or they cancel out in some manner. This then means that there is no acceleration. However, if a net force is present, this then means that the forces add up to something other than 0, then acceleration occurs. So then therefore an object moves at constant velocity unless acted upon by a net force. That's the description now of the law of inertia. So you can now summarize the law of inertia basically in the following manner. The law of inertia describes the cause of acceleration. Acceleration is caused by the presence of a net force. Acceleration is caused by the presence of a net force. This is as far as Galileo gets, getting the gist of it, if you will, in discovering the law of inertia. We now begin to move a little bit further, however. In the next series of lectures, I will go through the other 2 laws of motion that exist at a fundamental level, and this is where we begin to mathematically quantify the cause of acceleration by the presence of a net force.